Hello, I'm Oleksii Oleksenko and I'm presenting a joint project between the Technical University of Dresden and the Technion University. The topic of my talk today is Spectre. It's a vulnerability that appeared a few years ago and which bypassed many of the classical security mechanisms, but which still stays largely unpatched in real software. Specifically, I will concentrate on the bounce check bypass, the first version of Spectre, but the ideas that I present they will be also applicable to other versions of Spectre. So just to remind you what bounce check bypass is, here on the slide we see an example of this vulnerability. Here we have a buffer overflow which is patched by adding a bounce check, so a conditional branch that guards this memory access. This view can make a prediction on the outcome of this branch, and if this prediction is wrong, then this memory access will be executed even though it wasn't supposed to happen. This is called speculative execution. It's not visible into the software, so it doesn't change the behavior of the program or it doesn't influence the results of the program. However, it can leave certain traces on the hardware level. These traces can be later retrieved by the attacker, and some secrets can be leaked this way. So what has been done to patch this vulnerability? The SPIO vendors, they declared that the branch prediction is a feature, it's not a bug, and they are not going to release any hardware mitigations against this attack, at least in the nearest future. On the software side, we see a different picture from software to software. For example, browsers took it more seriously, such as Chrome. They implemented site isolation, they have sandbox and several other techniques. But if we look at the rest, then the picture is less reassuring. For example, in the Linux kernel, only about 170 array accesses are patched against Spectre. If you look, and that's in all of the source code base of Linux. Then if you look at OpenSSL, they declared that local attackers just not a part of their threat model. And even in the software where the local attacker is a part of the threat model, such as IntelliJX framework, Graphene, we see no patches against Spectre. So why is it the case? Why we see so little adoption of defenses? Because on one hand, they are quite expensive. A holistic mitigation against Spectre would slow down an application by about 50%, in some cases much more. And on the other hand, people are considering these attacks as more theoretical, which is arguable, but they are not willing to invest that much into mitigations against them. Therefore, the goal of our work was to change the situation, or at least help somehow in changing this situation. We wanted to improve the performance of the defenses against Spectre, and this way hopefully increase their adoption. And our solution to this, our approach, is to apply fuzzing. Fuzzing is a testing technique where you feed random inputs to a program until you detect an error in it. However, it is not as simple as taking one of the many existing fuzzing tools and applying it to a program. The problem is that even if a Spectre vulnerability is triggered during fuzzing, the fuzzer will not detect this vulnerability because speculative execution is an internal hardware feature and it doesn't show up on the software level. And our answer to this is what we call speculation exposure. The idea is to transform this speculative execution into normal execution. That is, we are transforming an internal hardware behavior into the software. We can do it through simulation. We can simulate a branch predictor, and in order to be on the safe side, to have an always correct simulation, we will simulate a branch predictor that always makes a wrong decision, that is, it goes into a wrong branch. However, running a full simulation would be way too slow. Therefore, instead, what we do a simulation inside the program. We are changing the program such that the speculative execution becomes a part of the program itself. Here's how we do it. Here's an example of a program. We have an entry node with a conditional branch that goes either into node B or C, and we transform this program in such a way that we duplicate this this entry node, and we replace the exit condition of this duplicated entry node with an inverse one. That is, we replace the conditional branch that existed before with a conditional branch that has an inverse condition. This way we are simulating a misprediction. However, just this would be insufficient. It would just break the program. We have to somehow preserve the state of the program. Therefore, before starting the simulation, we take a checkpoint of the program state, then we run the simulation, and after it we roll back the program to the previous state and we execute the original node with the correct conditional branch. So here's how it looks at runtime. We would execute the mispredicted branch first, we would roll back to the original node, and we will execute a correct branch next. So to summarize, speculation exposure means that we are transforming speculative attacks, something invisible to the software, into normal classical memory violation, something that is visible to software and that can be detected by fuzzers. And we implemented this idea of speculation exposure as a combination of an LLVM pass and a runtime library, and to detect these exposed vulnerabilities, we just used AddressSanitizer. Even though the idea of speculation exposure might sound quite simple, the implementation of it was actually quite tricky, because what we did here, we basically forced the program to execute wrong parts of the code. We forced it to go into the wrong paths, and it often led to crashes and similar things, so we have to deal with that. And in addition to that, we might have several mispredictions, several speculations in a row. We might have several conditional branches that are mispredicted. And simulating all of them creates a large tree of simulations, and it might lead to state explosion. However, I won't be going so much deeper into the details. If you are interested in them, you can read the paper. Instead, let's see what we can get with SpecFuzz. This table presents the results of our evaluation. Here we tested several libraries, several parsing libraries, because they deal directly with the user input and also OpenSSL, and the table presents the total number of vulnerabilities that we detected in those libraries. Since the number was actually pretty large, we decided to rank them somehow. We used certain heuristics to see whether some vulnerabilities are more dangerous than others. And here, each row in the table represents a different type of the vulnerability. The first row of vulnerabilities where the control flow of the program could be changed somehow. For example, if a code pointer can get overwritten or a return address can get speculatively overwritten. And the rest, the other three rows, are the cases where we would have either a speculative write or a read to an invalid object. The second row, controlled vulnerabilities, are the cases where the attacker can control the accessed address, therefore we consider them more dangerous. And the third row, uncontrolled, these are the cases where the address is always the same, the accessed address. The last row are the cases where we didn't have enough information to decide a type. Yet patching all these vulnerabilities manually would be way too tedious and going manually through all of them. Therefore, instead, we implemented a mechanism to patch them automatically. So what we did, we took two existing patching techniques. One of them is an LLVM pass that adds L-fences after conditional branches, and the second technique is what is called speculative load hardening. It's a technique that adds data dependencies. And we modified these two tools to accept a list of vulnerabilities that we received from fuzzing, and also a coverage from fuzzing. And what we did here, we removed the hardening from all the cases where we had enough coverage and where we did not detect the vulnerabilities. So what we have here in effect is we are cleaning up the hardening from the program with the fuzzing. And here's what we can get out of it. So this plot represents the speed up, that is how much faster a program becomes when we apply this partial hardening in comparison to full hardening, where every conditional branch is patched. Again, we tested several libraries, and here are the results. Here the green bar is L-fences, and the blue bar is modified speculative load hardening. As you see, the results are quite different. In some libraries, the speed up was very, very considerable, and we had quite beneficial results. But with OpenSSL, for example, the results are not as big and not as impressive. This happened, so the lower effectiveness fuzzing happened here because we had quite low coverage with OpenSSL, only about 20-25%, and we also detected several vulnerabilities on the hot path of the program. So in summary, here's how we use SpecFuzz. Initially, you have the source code of a program written in C or C++. You compile it with our modified version of LLVM that applies speculation exposure, that adds speculation exposure. Then you fuzz the resulting binary, you get a list of vulnerabilities, you analyze them, aggregate, and you feed them to our automated patching tool. And in the end, as a result, you get a hardened binary against Spectre. And with that, I want to conclude, and I hope that our work will make, indeed, the defenses against Spectre more appealing and increase their adoption in security-critical applications. If you want to try, the source code is published on GitHub, and if you have any questions, just write us. Thank you.